Hello, in this video I'd like to build off of a previous video that I've made on Ehrenfeucht-Fraïssé games on linear orderings, specifically the last slide of that video. I'll try my best to make sure that this video is self-contained, but if you want, now might be a good time to go back and watch that previous video. Specifically, in this video, I'd like to explore what happens when we play Ehrenfeucht-Fraïssé games on the natural numbers as a linear ordering. Ehrenfeucht-Fraïssé games are an extremely powerful tool within model theory that allow us to talk about formulas that two structures have in common or formulas that differentiate two structures. My goal with this video is to provide a complete classification of the non-standard models of the natural numbers as a linear ordering. My hope with this video series is to eventually explore the non-standard models of some of our regular language structures, such as the weak second-order theory of one successor. But in order to be able to reason about that structure, which can reason about the natural numbers as a linear ordering, we need to first understand this simpler structure. What do its non-standard models look like? How can we axiomatize it? What formulas are true and what formulas are false for this particular structure here? My goal is to introduce these tools and notations applied to some simpler structures before we go about applying these tools to the more complicated weak S1S. So what is an Ehrenfeucht-Fraïssé game? So whenever we specify an Ehrenfeucht-Fraïssé game, we're always going to want to specify the length of the game, and as far as I'm concerned, that's going to be some finite number. There is value in studying Ehrenfeucht-Fraïssé games of various infinite lengths, but those are tools for studying infinitary logics, and I'm interested in first-order logic, which is a finite logic. All of the formulas in this logic are finite. So we're always going to want to restrict the length of the game to be some finite n. And the game is going to be played on a game board, and the board is going to consist of two structures, m and n, and these two structures are going to have finitely many relations to them. So, for instance, this structure here has one relation to it. So that's what we're looking for. In the next video, I'll talk about what happens if you want to play the Ehrenfeucht-Fraïssé games on structures that have operations to them, or constants, or infinitely many relations. Things get a little bit trickier in those cases. These games have two players to them that play very asymmetric roles. The first player, who's sometimes called player 1, is called spoiler, and the second player, sometimes called player 2, is called duplicator. On each turn, spoiler will first pick an element of either m or n, and then duplicator will match that element with an element of the other structure. Together, this is going to give us a sequence of elements of the two structures. We'll let xi denote the element of m that gets picked on turn I, regardless of who picks it. And we'll let yi denote the element of n that gets picked on turn I. Again, it doesn't matter whether on turn 2 spoiler picked x2 within m and duplicator matched it to y2 within n, or if spoiler picked y2 in n and duplicator matched it to x2 in m. We don't care who picked what, we just care about which elements in the two structures got matched together. Together, this matching has to be a finite partial isomorphism. In particular, if we restrict our attention to just these elements of m and just these elements of n, hence the partial, then this matching has to be an isomorphism. Specifically, it needs to be the case that if any atomic formula is true of the elements in this structure, it also has to be true of the elements that got matched when we do the translation in the other structure. And this just needs to be true for atomic formulas. So if we're restricting our attention to the natural numbers with less than or equal to, it has to be the case that if x1 is greater than or equal to x3, then it needs to be the case that y1 is greater than or equal to y3. For the particular elements x1, x3, y1, and y3 that wound up getting matched. We say that spoiler wins the game if at any point they can force this to not be a partial isomorphism. And as soon as it's not a partial isomorphism, as soon as there's an atomic formula that holds of some of the elements up here that doesn't hold of the same elements down here, or vice versa, then we can call the game done. We don't have to worry about finishing the game all the way up to length n. It's definitely the case that spoiler has won this game. On the other hand, if duplicator is able to last for n turns, then duplicator is said to have won the game. The following fact is what makes Ehrenfeucht-Fraïssé games useful. Spoiler wins this particular game if and only if there is a first-order logical formula, phi, of quantifier depth less than or equal to n, distinguishing these two structures. Phi is not going to have any free variables, so we could call it a sentence. Quantifier depth is a particular way of measuring the length of any first-order logical formula. Specifically, it measures the maximum number of quantifiers that are active at any one time within the formula. There's a very nice recursive way of calculating the quantifier depth of any formula. If we have an atomic formula, it has a quantifier depth of 0 because it doesn't have any quantifiers in it. If we have a formula of the form not phi, then we haven't added any quantifiers, and so it has the same quantifier depth as phi. If we have a formula of the form phi and rho, or phi or rho, then the quantifier depth is going to be the maximum of the quantifier depth of phi and rho. And then finally, if we introduce a quantifier, then that increases the quantifier depth by 1. And so one can recursively compute the quantifier depth of any first-order logical formula in this way. Very often, we're not so much concerned about the quantifier depth of a formula distinguishing these two structures, right? A formula that's true of m, but not true of n, or that's vice versa, true of n and not true of m. Very often, we're not so much interested in the quantifier depth of that formula, but whether there exists a formula of that form at all. Remember that we're interested in structures that are logically equivalent to the natural numbers with less than or equal to, and so we would like to find structures where there is no distinguishing formula for any quantifier depth n. And so what we're looking for is we're looking for a situation where spoiler never has a winning strategy on the Ehrenfeucht-Fraïssé game of length n for any n. Let's do a really basic example. Let's take a look at some structures that don't have any structure to them. They just have elements. So let M be the set containing 0 and 1, and N be the set containing 0, 1, and 2. We can visualize this game like this. We have our 2 elements of N up here, and our 3 elements of M down here, and we would like to match them together. Let's say that spoiler, on their first turn, picks this element here. Then duplicator must match this element to one of these elements down here. Let's say that duplicator picks 1. It's sometimes convenient to keep track of the xi and yi. In this case, x1 is 0, the element of n that got matched on turn 1, and y1 is 1, the element of m that got matched on turn 1. Now let's say that spoiler plays at 1 within m. That means that y2 is going to be equal to 1. And so therefore in m we have the fact that y1 is equal to y2. That's an atomic formula. Even though these structures don't have any structure to them, don't have any relations to them, we've decided that equality is always available within the first-order logic of any structure. So it needs to be the case that duplicator picks an x2 within n in order to make the translated version of this formula true within n. That forces duplicator's hand. Duplicator must play at 0. And so spoiler has wasted their turn. We haven't made any new matchings, and so that isn't going to make any more atomic formulas true of one structure and false of the other. Let's say that spoiler instead plays at 0 within m. Duplicator does not have a choice as to what to match it to. Duplicator must match this 0 to this 1 here. Suppose instead that Duplicator matched this 0 to this 0. Well, then it would be the case that x1 was equal to x2, but y1 was not equal to y2. And so we would have an atomic formula that was true in n, where the translated version was not true in m. Duplicator will have lost. So just like how Spoiler wants to avoid playing at an already matched vertex, Duplicator also wants to avoid playing at an already matched vertex. Instead, Duplicator is going to match this 0 down here to this 1 up here. Then it's going to be the case that x1 is not equal to x2 and y1 is not equal to y2. These two structures with this particular matching agree on their atomic formulas, and so the game is allowed to continue. Finally, Spoiler plays here at 2 within M, and Duplicator has nowhere they can match it to without breaking this constraint, without accidentally making it so that we have an atomic formula that's true in one structure but not true in the other. Specifically, if Duplicator picks 1 to match 2 to, it's going to be the case that x2 is equal to x3, but y2 is not equal to y3, and so we have an atomic formula that's true of one structure that's not true when we do our translation. At this point, no matter what Duplicator does, they've lost. Now, I've actually forgotten to specify how long this game lasts. If the game only lasted 2 turns, well, then Duplicator can win. Nothing that Spoiler could do could prevent Duplicator from being able to make a matching on their second turn. And so if this was the Ehrenfeucht-Fraïssé game on 2 turns, then Duplicator would definitely win and Spoiler would not be able to win. On the other hand, when we introduced a 3rd turn, Duplicator definitely lost. And you can do a little bit of reasoning to show that if Spoiler and Duplicator are playing optimally, then this is what happens. In the game of length 2, Duplicator can definitely win, and in the game of length 3, Spoiler can definitely win. It's often the case that a player's optimal strategy doesn't depend on the number of turns of the game. But we'll actually see an instance later on in this video where the length of the game is important information in determining one of the player's strategies. Still, for this case, knowing the length of the game doesn't affect either player's strategy. By our fact about Ehrenfeucht-Fraïssé games, the fact that Spoiler wins the game of length 3 tells us that there is a formula, a sentence of quantifier depth 3, that's true of one structure and false of the other, that distinguishes the two structures. If you like, you can take a moment to try to figure out what that sentence is. So that sentence is that within M, there exists an x, there exists a y, and there exists a z, such that x is not equal to y, and y is not equal to z, and x is not equal to z. If we negate this, for any x, for any y, and for any z, x is equal to y, or y is equal to z, or x is equal to z. And this is true within n. This here is the difference between these two structures. On the other hand, we've also shown, because Spoiler does not have a winning strategy on the game of length 2, that these are in some sense the shortest formulas, in terms of quantifier depth specifically. We can't have a formula of quantifier depth 2 that distinguishes these two structures. Every formula of quantifier depth 2 that's true of n is also true of m, and vice versa. Even in the case where we only have equality, actually enumerating all of the formulas of quantifier depth 2 is a very difficult task. Well, there'll actually be infinitely many of them, but they'll have a bunch of redundancy in them, right? You'll have formulas that are combined using and or with themselves. And so you can kind of simplify those away. And so writing all of those formulas out and actually checking that they're true of n if and only if they're true of m is quite a difficult task, but we can prove this fact that these two structures all agree on their quantifier depth 2 formulas using the fundamental fact about Ehrenfeucht-Fraïssé games. Let's now add a little bit of structure to our structures. Let's make them linear orderings. Let's say that M is the set containing 0 and 1, but now we can talk about these two elements being less than or equal to each other. And the same with N. It's very common within the study of linear orderings and set theory in general to denote this set here, the set containing 0 and 1, as 2. This is somehow the canonical set of size 2. And so we would write this as 2 with less than or equal to, and if we knew that we were studying linear orderings, well, we would just call this structure 2. And then similarly, this structure here we can denote as just 3, or 3 with a notion of less than or equal to. Again, we can set up the same sort of graphical representation of our game board, but now there are extra constraints on the moves that we can make. Let's say that Spoiler starts out by playing at 0 within N, and Duplicator matches it to 1 within M. That means that x1 is going to be equal to 1 within M, and y1 is going to be equal to 0 within N. Now let's say that Spoiler plays at 0 within M. Duplicator can't match this 0 to this 0 here, because then y1 would be equal to y2, but x1 wouldn't be equal to x2. So again, we would have an atomic formula differentiating the two structures. On the other hand, Duplicator also can't match this 0 to this 2 here, because then we would have the atomic formula up here that x1 is greater than or equal to x2, but not the corresponding atomic formula down here, right? It's not the case that y1 is greater than or equal to y2. So Duplicator has lost on turn 2. Is this necessarily the case? If Spoiler and Duplicator play optimally, can Duplicator last longer? Can Spoiler force the game to end earlier? And more generally speaking, if we have two finite linear orderings, finite sets with the natural ordering on them, what is the optimal strategy and how long do the games last? I'll link a resource down below where you can play this game for yourself on finite linear orderings, either against yourself or against an AI that plays optimally. And you can see if you can figure out any patterns. So it turns out that Spoiler actually does have a winning strategy on this game here that wins in 2 turns, provided that Spoiler starts by playing here, at the middle point within our 3-point linear ordering. No matter where Duplicator matches it to, it's essentially the same thing, but it's going to be mirrored. So let's say that Duplicator matches to 0. Then it's going to be the case that there's one side where there's nothing to match to. So Spoiler plays at 0 within N, and Duplicator can't match it to anything within M. The game is over, and the game has ended in 2 turns, because there's a formula of quantifier depth 2 that's true of one of these structures that's not true of the other, that distinguishes the 2 structures. I'll let you take a moment to try to figure out what that formula is. So it turns out we can actually read the distinction between these 2 structures off of Spoiler's winning strategy. Spoiler took advantage of the fact that there was an element in N that had an element greater than it and an element less than it, and there's no such element within M. Specifically, we can write this out as saying that there exists a y1 such that there exists a y2 such that y2 is greater than, I guess we want it to be strictly greater than, which is just the same as saying greater than or equal to and not equal to. y2 is strictly greater than y1, and there exists a y2 such that y2 is strictly less than y1. I usually consider it bad form to use the same variable twice in the same formula, but I hope this makes a connection between the game and the formula. Spoiler can pick a y1 such that there is a place to play on turn 2 where y2 is greater than y1, and there's also a place to play on turn 2 where y2 is less than y1. On the other hand, that's not going to be true within M. For any x1 that duplicator matches this original y1 to, it's going to be the case that either every x2 is less than or equal to x1, or every x2 is greater than or equal to x1. It's either going to be the case that duplicator played at the maximal element or duplicator played at the minimal element. In case duplicator played at the maximal element, there would be a y2 that spoiler could match it to that was strictly greater than y1. And in case duplicator plays as they did at the minimal element, there would be a y2 strictly less than y1 that spoiler could match over here, which is what they did. This is actually one of the more complicated differences to read off as a formula because spoiler needs to adapt their strategy depending on where duplicator plays. This adapting of strategies winds up looking like ands and ors, depending on who's adapting their strategy within which structure. You can see some simpler translations of strategies to formulas in my previous Ehrenfeucht-Fraïssé games on linear orderings videos linked down below. Notice that this difference is one quantifier fewer when we added this extra structure here. Adding more structure gives us more formulas, which potentially makes it easier to distinguish our two structures, and in this case it did. We were able to distinguish our two structures in a formula of quantifier depth 2, whereas when we didn't have less than or equal to, we required formulas of quantifier depth 3 in order to distinguish our structures. Let's suppose now that M is a 6-point linear ordering and N is a 7-point linear ordering. How many turns does it take for spoiler to win the game? How many turns can duplicator last? I'll let you take a moment if you would like to try to play this game for yourself. So spoiler's optimal strategy is to start off by playing at the middle element of N. Duplicator must match it to some element of M, and it turns out they're going to want to match it to an element somewhere in the middle of M. You have to go and kind of handle separately the cases where duplicator plays at either 1 or 4, which are the same by reflection, or at 0 or 5, which are the same by reflection. You have to handle those cases separately if you want to prove that this is in fact an optimal strategy, but it's not that hard to do so. At this point, we've separated the game board into 2 game boards. One that has 3 elements on top and 3 elements on the bottom, and one that has 2 elements on top and 3 elements on the bottom. This is particular to linear orderings. This doesn't necessarily happen in other sorts of structures where there might be additional relationships between elements on one side of a point and on the other side of a point, or if it doesn't even make sense to talk about things being on one side of a point or another side of a point. The Ehrenfeucht-Fraïssé game on the right-hand side, where there's 3 points on top and 3 points on the bottom, is an easy win for duplicator. They just sit back and match up points with the corresponding points. Whatever spoiler picks, duplicator just matches it with the corresponding point, and of course duplicator is going to win because these 2 linear orderings are isomorphic. They aren't distinguishable with formulas of any quantifier depth. On the other hand, we already know what happens on the game on the left-hand side, where there's 2 points here on the top linear ordering and 3 points here on the bottom linear ordering. We know that duplicator can last 1 turn, but can't last 2 turns, specifically because spoiler will play here. So Spoiler's sensible thing to do next is to not play on the right-hand side, but to play on the left-hand side, and to pick this point here. Again, duplicator matches it to either of these points, and then on the next turn, Spoiler plays here, and duplicator has lost. After now 3 turns. This is optimal, and I hope I've given you a sense of how to prove that it's optimal. So that means that these two structures agree with each other on any formulas of quantifier depth 2, but they disagree on a particular formula of quantifier depth 3. Here's the formula and its negation. The formula is true of n, and its negation is true of m. This motivates us to do a proof by induction, which I encourage you to take a moment to pause and try to work it out for yourself if you want. So one can prove that orderings up to size 2 to the n-1 are all distinguishable with quantifier depth n. So if we have two numbers that are less than or equal to 2 to the n-1, and we take the linear orderings of those sizes, we can find a formula of quantifier depth n that distinguishes those two structures. In particular, this means that the EF game between those two structures is going to be won by Spoiler by turn n. On the other hand, if we have two numbers that are 2 to the n-1 or larger, those two linear orderings are going to be indistinguishable by formulas with quantifier depth n. In other words, duplicator is going to be able to win the game of length n on those two structures. So if we're looking at games of length 0, and duplicator is always able to win games of length 0, duplicator is able to hold out for 0 turns within any game. That means that Spoiler isn't able to distinguish any structures from any other structures. And this agrees with what we have up here. The orderings up to size 0 are all distinguishable from each other, but then orderings of size 0 or larger are indistinguishable from each other. So orderings of size 0 or larger are all indistinguishable from each other. On the other hand, with a game of length 1, well, there's going to be something slightly different if one of the structures has 0 elements in it. In particular, duplicator or Spoiler won't have anywhere to play in that structure. And so all of the orderings up to size 1 are going to be distinguishable from each other. So we can distinguish 0 from 1. I won't connect them to indicate that they're distinguishable from each other. On the other hand, all orderings of size 1 or larger are going to be indistinguishable with just one turn. So I'll connect these numbers to indicate that they're indistinguishable from each other. If we have 2 turns, orderings up to size 3 are all going to be distinguishable from each other. So we can distinguish 0 from 1, from 2, and from 3. These are all different linear orderings, and we can find formulas of quantifier depth 2 that distinguish them all from each other. On the other hand, orderings of size 3 or larger are all going to be indistinguishable from each other. So we aren't going to be able to distinguish 3 from 4, or 3 from 5, or 4 from 5, or so on and so forth. So any two numbers within this region are going to be indistinguishable from each other in 2 turns. In 3 turns, we're able to distinguish orderings up to size 7 from each other, and then orderings of size 7 or larger are all going to be indistinguishable from each other. So orderings of size 7 and size 8 are going to be indistinguishable, and so on and so forth. Given a particular formula phi, it's useful to talk about whether that formula is true of this bit here, where they're all eventually indistinguishable, right? If they're indistinguishable, any formula is either true or false of all of these structures. And so if we have a formula of quantifier depth 2, we can ask, is this one of those formulas that's true of all of the finite linear orderings of size 3 or larger? Or is it not one of the formulas that's true? Is its negation one of the formulas that's true of all linear orderings of size 3 or larger? And of course, where we need to start looking depends on the particular formula. If we have a formula of quantifier depth 3, we're going to want to start looking at 7 or larger, right? We would ask, is this one of those formulas that's true of finite linear orderings of size 7 or larger? All of these formulas that are eventually true are also true of the linear ordering omega plus omega star. This linear ordering is a copy of the natural numbers followed by, right? We use addition to indicate the followed by operation for linear orderings, followed by the negative natural numbers, or a reversal of the natural numbers. So this is a bit of a non-traditional ordering on the integers, but it gives us a sense of what this ordering looks like. We can also visually represent it like this. This is my favorite linear ordering. It winds up satisfying all of the first-order logical properties that are true of sufficiently large finite linear orderings. It, in some sense, behaves a lot like a finite linear ordering, right? It's got a first element, it's got a last element. Every element has an element immediately before it and immediately after it, but it's infinite, and it's infinite in the middle. And the way that one proves this is very straightforward. One just adds into the proof by induction here the additional fact that these really large linear orderings are also indistinguishable from omega plus omega star. This proof actually has some tricky case handling in it, so I'll give you an overview of what it looks like. Suppose that we're trying to prove the specific case that the 7-point linear ordering is indistinguishable from omega plus omega star in 3 turns. Given that all finite linear orderings of size 3 or larger are indistinguishable from each other and indistinguishable from omega plus omega star in 2 turns. That's our inductive hypothesis. Well, we need to handle all possible cases. What happens if spoiler plays somewhere like here? Well, duplicator should play here. In order that we divide the board up into 2 parts. One game is a 1-point linear ordering versus a 1-point linear ordering. Duplicator wins on that game. And then the other one is a large linear ordering, an ordering of size 3 or larger, versus omega plus omega star. And now, because 1 turn has been taken up, we only have 2 turns remaining. In this case, we use the inductive hypothesis that finite linear orderings of size 3 or larger are indistinguishable from omega plus omega star in 2 turns. On the other hand, if spoiler plays a fair bit into the omega star bit, then duplicator is actually going to want to match it up to the middle point on the top linear ordering. This divides the game board up into 2 game boards. One which is a 3-point linear ordering versus a 5-point linear ordering. And again, by the inductive hypothesis, duplicator can survive for 2 turns on this particular game. On the other side, we have a 3-point linear ordering versus omega plus omega star, and again, by our inductive hypothesis, duplicator can last 2 turns on that particular game. Of course, if spoiler splits their attention between these 2 game boards, that's not going to work out in their favor. Every turn when the game board gets split into 2 halves, spoiler is always going to want to identify the side that they think that they can win most quickly on, and play exclusively on that side. The cases where spoiler plays on the omega part of omega plus omega star are similar. So that just leaves us with the case where spoiler plays on the finite linear ordering, and then we just have to be a little bit careful. If spoiler plays here, we're going to want duplicator to play here, so that we have a game board of size 2 versus a game board of size 2, and a game board of size 4 versus omega plus omega star. And again, this situation works out in duplicator's favor by the inductive hypothesis. So I'll let you fill in the gaps of the proof if you want and make it fully general, work for any n, but that's essentially what's going on. So we're finally at a point where we can determine what the non-standard models of the natural numbers as a linear ordering look like. We already got a sense from the previous video that these linear orderings necessarily look like the natural numbers followed by some number of copies, potentially quite infinite, of the integers. And we can formalize this proof as follows. Suppose that we have a non-standard model of the natural numbers as a linear ordering. Because we know these facts are true of the natural numbers as a linear ordering, and they can be written in first-order logic, we know that this structure here necessarily has a smallest element, no largest element, and every element except the smallest element has an element immediately before it, and every element has an element immediately after it. Let's consider a collection of elements I, where the elements of that collection are required to be infinitely far away from each other. So there have to be infinitely many elements between any two different elements of I within M. And we'll also require that these elements be infinitely far away from 0. So they can't be 0 or the immediate successor of 0 or the immediate successor of that, and so on and so forth. And we'll let I be a maximal such collection. We know that M must have a minimal element and a successor to that minimal element, and a successor to that, and a successor to that, and so on and so forth. Let's give them these names, but they might be named something else within M, and so on and so forth. And then we also have our elements of I. So let's say C0 is one of the elements of I, and we know that, I don't know, C1 is maybe another element of I, and so on and so forth. And then we know that C0 necessarily has an element immediately before it and immediately after it, and so on and so forth. And we know that none of these elements are these elements or these elements because of our requirement that I be a collection of elements that are infinitely far from each other and infinitely far from 0. And so just as before, we wind up getting a linear ordering that looks like the natural numbers followed by some number of copies of the integers. Where again, it could be possible that I is quite an infinite set that has its own interesting ordering on it within M. So this might be, you know, one copy of the integers for every rational number, or for every real number, or for every natural number, or for every negative natural number. And you might, of course, ask, could there be any other elements of M? Have we actually captured all of the different elements of M? And the answer is yes. If there's some element that we haven't captured here, then it would be an element that we could add into I to make it a larger collection of elements that were infinitely far from each other and infinitely far from 0. And we've already said that I is maximal such collection of elements. So this tells us that every non-standard model of the natural numbers as a linear ordering has to look like the natural numbers followed by some number of copies of the integers. In other words, a woozle. And again, L might be a fairly complicated linear ordering. I'll put an example on the screen of some instances of fairly complicated woozles for fairly complicated linear orderings L. But again, we can ask whether or not this is an exact characterization. We know that every linear ordering that is logically equivalent to the natural numbers is of this form, but we haven't shown yet that every linear ordering of this form necessarily is logically equivalent to the natural numbers with less than or equal to. It might be the case that we only get this logical equivalence for some specific linear orderings L. But it turns out that isn't the case. Woozles are logically equivalent to the natural numbers with less than or equal to, regardless of what L is. And we can prove this using Ehrenfeucht-Fraïssé games. So let's play an Ehrenfeucht-Fraïssé game between a particular woozle and the natural numbers. So my claim is that if we're playing the EF game of length n between the natural numbers and a woozle, then Duplicator has a winning strategy. They have a strategy that will allow them to survive for n turns. What does this strategy look like? Well, it depends on where Spoiler plays. If Spoiler plays at some point in omega, then Duplicator can just match it with the corresponding point in the omega part of the woozle. This divides the game up into two game boards. One, which is, in this case, 2 elements versus 2 elements, which Duplicator can last arbitrarily long on. And then the other one, this part of omega, it still looks like omega. So we have a game board that's omega versus this part of omega still looks like omega. So it's omega versus omega plus z times L. So this half of the game actually looks identical to the original game. Spoiler hasn't made any progress whatsoever, and we can use our inductive hypothesis to tell us that Duplicator can last the remainder of the game, the remaining n-1 turns, on this game board, on this side of the game board as well. And again, it doesn't make sense for Spoiler to split their attention between the left side of this matching and the right side of this matching. Similarly, if Spoiler plays at one of these points in the omega part of the woozle, then Duplicator can just match it to the corresponding point in omega. And again, we have the same sort of situation. The only interesting case is if Spoiler plays at one of the points in one of the z parts of a woozle. Then Duplicator must match this point to a sufficiently large element of omega. Let's just call it k for now, but of course we can tell exactly what size this point has to be by the constraints that it has to satisfy. The resulting games are a game between omega and omega, right? The elements after this element here are going to form a copy of omega, followed by some number of copies of z, a different number, right? A different L, but it's going to be, a woozle for some L. So we have omega versus a woozle, which again we apply our inductive hypothesis for. On the other hand, we have some large finite linear ordering versus a linear ordering of the form omega plus, potentially there are some copies of z between here and here. So it might be some number of copies of z plus the points before this in this z part, which are going to look like omega star, which we have to expand our induction that we did a little bit more in order to get that this particular linear ordering is indistinguishable from sufficiently large finite linear orderings. And all Duplicator had to do was pick this k so that this linear ordering was large enough to be able to use this fact. Now, of course, in order to pick that k, Duplicator needs to know how many turns left there are in the game. This is important. If Duplicator wants to last forever, they can't. No matter what k here Duplicator picks to match this element to, there's only going to be finitely many elements up here less than k, and there's going to be infinitely many elements down here that are less than c0 minus 1. And so Spoiler can just go through and one by one pick these elements, or maybe do something a little bit more efficient, and Duplicator is eventually going to run out of things to match them to. So Duplicator is eventually doomed, but the important part is that Duplicator only has to last n turns, and Duplicator knows how many turns that is. So if you suddenly change up the game on Duplicator and say, oh no, you need to last many more turns than this, then duplicator is a bit sunk. They've made a bad choice. They should have picked a larger k. But that's not how Ehrenfeucht-Fraïssé games work. You're always allowed to know exactly how long the game is going to last at the very beginning of the game. This is because we're interested in studying exactly the formulas of quantifier depth n that differentiate the two structures. It's only then later that we say this argument works for any n, and therefore there's no formula of any quantifier depth distinguishing these two structures. Now, I want to take a moment to appreciate what we've done here. Remember that we showed that every linear ordering that satisfied these properties is necessarily a woozle, and therefore logically equivalent to omega. In other words, these properties here are enough to determine the truth or falsehood of every logical property that these structures could satisfy. Once we know that a structure satisfies these properties, we know that all of the properties that are true of omega are true of that structure, and all of the properties that are false of omega are false of that structure. In other words, these properties here form an axiomatization. They tell us everything we need to know about this class of linear orderings that are all logically equivalent to each other, including omega. We have axiomatized omega as a linear ordering, or the natural numbers as a linear ordering. This might seem a little bit fishy. When I've talked about axiomatizations before, I've talked about using axioms in order to prove things using proofs, right? Step-by-step arguments where any step of the argument can either be an axiom or a valid deduction from previous lines of the argument. But if you remember from our compactness video, the question of whether or not a structure exists is equivalent to the question of whether or not a set of sentences is consistent in the proof sense. In other words, suppose that we have our axiomatization, let's just call it A. We can of course AND together all of the formulas in our axiomatization and get a single formula, so you could refer to that formula as A. Suppose that we have some other formula, phi. Then we know that one of the following is true of omega, is true of the natural numbers, either A and phi or A and not phi, depending on whether phi is true of omega or not. Only one of these two formulas is actually going to have any models. If phi is true of omega, then A and phi is true of omega and therefore true of all of the woozles and therefore has a bunch of models. But that means that not phi is not true of omega and therefore not true of any of the woozles, and so not true of anything. Because the only structures that satisfied A, our axiomatization, were woozles. I guess I should mention that omega is a woozle, right? It's the woozle where L is the empty linear ordering. So one of these two formulas doesn't have any models. And so by the converse of the compactness theorem, one of these two formulas proves a contradiction. In other words, if our proof system has a robust enough way of reasoning about proofs by contradiction, it's necessarily the case that, let's say that this is the one that produces a contradiction, it's necessarily the case that we can prove from this a contradiction, and so if A is true, then phi has to be true in order to avoid A and not phi being true. So in other words, A implies phi, logically speaking, from the notion of proof. That's the really clever thing. Compactness allows us to go back and forth between this question of whether or not models exist and formal notions of proofs within a sufficiently robust proof system. It also allows us to not care too much about the specific details of those proof systems. So just to recap, in this video we have completely classified what all of the non-standard models of the natural numbers as a linear ordering look like, as well as provided a complete axiomatization of this structure, a set of formulas from which all others follow logically. I hope you can appreciate now just how powerful Ehrenfeucht-Fraïssé games can be. In the next video, I'll talk about how we can apply Ehrenfeucht-Fraïssé games to other structures besides just relational structures. For now, you might want to take a look at my video on Ehrenfeucht-Fraïssé games on graphs, which are another type of relational structures. They play almost exactly the same way. The key thing is, though, that with linear orderings, whenever we played the game, it split the board into two parts, and that made things a lot easier to analyze. Whereas on graphs, that's not the case. But otherwise, they're exactly the same games. They can be used to show that certain graphs are logically distinguishable from each other and logically indistinguishable from each other with particular quantifier depth n in the language of graphs. And graphs are very general, and so hopefully that can give you a sense of what EF games look like on arbitrary relational structures. So that's it for this video. Let me know if you have any questions or comments down below, and I hope to see you in a future video.